Welcome everyone in 7th week of the course in which we are discussing chapter 11 of the book. Today we are exploring the architectural evolution of state of the art language models, tracking how we moved from early sequence to sequence models to modern systems like BERT. As shown in the system initialization diagram on the left, modern text processing pipelines intake sequential data and route it through stacked encoder layers, multi-headed attention pathways, and targeted decoder blocks. This architectural transition has completely redefined how neural networks map linguistic structures, allowing models to scale beyond simple next token processing into deep bidirectional contextual understanding. Let's look at standard sequence to sequence modeling, which forms the foundation of machine translation. The pipeline is split into two major blocks, the encoder and the decoder. First, the encoder processes a varying length input sequence, like our English text, learning natural language processing, one LSTM cell at a time. It compresses this entire phrase into a single fixed length context vector, often called a thought vector. The decoder then takes this solitary vector along with the start token to generate the target French translation token by token until it hits the end token. We see the structural Keras blueprints for implementing this architecture. In the encoder blueprint, it is critical that we set return state is equal to true inside our LSTM layer. This explicitly captures the final hidden state and memory cell which together compose our information packed context vector. In the decoder blueprint, we employ a technique called teacher forcing. During training, the decoder doesn't guess blindly, it initializes its state directly with the encoder's context states and uses the true target tokens from the previous step to predict the next word, stabilizing the learning process. The upper graphic illustrates the problem. The information bottleneck. When forced to compress long, complex sentences into a single, fixed length context vector, early words are forgotten, causing the vector to literally fracture under data load. The solution is the attention mechanism, which is shown below. Instead of a single vector, attention passes all encoder hidden states to the decoder. At each generation step, a scoring function computes relevance weights. This dynamically dictates which specific input words the model should focus on most to accurately output the current token. The transformer architecture replaces sequential recurrent loops entirely with parallel processing. Looking at the macro view, the model coordinates 6 stacked encoder layers directly with 6 stacked decoder layers, allowing context to flow universally. In the micro view inside an encoder, we see the internal sublayers. Self-attention allows each token to evaluate every other token simultaneously. This passes through residual connections and layer normalization to prevent gradient decay and goes into a feed-forward network to project embeddings into higher dimensional space, drastically optimizing training speed. Let's dissect the core engine driving the transformer. The self-attention mechanism for every input token, like natural and language, the model multiplies its embedding by trained weight matrices to create three distinct vectors, a query q, a key k, and a value v. To determine contextual weight, a token multiplies its own query vector by every other token's key vector. These scores are scaled, normalized via softmax, and multiplied by the value vectors. High attention scores directly dictate which informational values are pulled into the token's final representation. Building on the transformer encoder, BERT introduces true bidirectional transfer learning. Unlike past models that read text strictly left to right, BERT trains on unlabeled text using two unique strategies. First, masked language modeling, where it hides 15% of input tokens and forces the model to predict them using both left and right context. Second, next sentence prediction, which trains the model to understand pair relationships by determining if sentence B logically follows sentence A. This is backed by a rich embedding stack combining token, segment, and positional data. We conclude with the incredible versatility of BERT fine tuning. Because the core architecture is pre trained on massive datasets, we can append a single, simple output layer to solve diverse downstream applications. For single sentence classification, like sentiment analysis, we feed the specialized CLS token output into a dense layer. For sentence pair tasks like question answering, we use SCP tokens to split sentences and analyze their relationship. Finally, for named entity recognition, we utilize every individual positional output vector simultaneously to label specific word in real time. I hope that you have enjoyed all the lectures of the natural language processing. Thank you.